In the last video, we introduced the concept of electrophilic aromatic substitution, or EAS for short, the reaction where we take an aromatic ring, benzene, and we react it with an electrophile to ultimately substitute one of the hydrogen atoms from the ring for an electrophile, such as a nitro group, NO2, in the case of the EAS reaction that we're going to focus on in this video, which is the so-called nitration reaction. I've written out the general nitration reaction here for you, where we take benzene as our starting material, react it with, and here's where it gets kind of weird, a mixture of nitric acid and sulfuric acid in order to yield, ultimately, the attachment of a nitro group replacing one of the hydrogens on the aromatic ring. So we're going to tackle in this video the reaction mechanism that occurs in order to carry out this transformation, explaining during the course of that why we have this mixture of sulfuric acid and nitric acid as our reactant, using the mechanism to explain how this all works. Let's go ahead and take a look at this. In the last video, we learned about three general steps that occur in electrophilic aromatic substitution reaction mechanisms. The first step is the step that is specific to each individual reaction type, and that is generating a better electrophile, or generating a stronger electrophile. For example, by reacting the initial electrophile with some catalyst to further activate that electrophile, making the electrophile, in other words, more electrophilic, more strongly positively polarized, or enabling that electrophile to carry a positive formal charge that will make that electrophile very strongly attractive toward a nucleophile. Second step of the reaction general mechanism for all electrophilic aromatic substitution reactions that we will look at is that the pi bond from the aromatic ring is going to attack the electrophile. So pi bond from the aromatic ring attacks the electrophile. And the product of that particular step is what we refer to as an Arenium ion. That was the intermediate where the aromaticity has been disrupted and we have a positively charged carbon at one of the positions of the originally aromatic ring. We call that the Arenium ion. And then finally, the third general step in these mechanisms is the loss of a proton from the Arenium ion in order to restore aromaticity. So we lose a proton in this elimination type reaction from the Arenium to restore aromaticity. So what we are going to do for this reaction, the nitration reaction that we're focusing on here, is we are going to look at how we apply these three general steps to our specific scenario of a nitration reaction. So taking a look at the reactants that we'll work with here, for right now and for the next several videos, we're going to be starting with benzene as our aromatic reactant. When we get into some of the later parts of this chapter, we'll transition into looking at substituted benzene derivative reactions, such as if we start with toluene, how does that impact the reaction? Or if we start with phenol, how does that influence the course of the reaction and things like that? But for now, we're just focused on the fundamentals here of starting with benzene. We are going to react it with sulfuric acid, H2SO4, mixed with nitric acid, and the formula for nitric acid being HNO3. The product of that reaction, anytime you take a mixture of nitric acid and sulfuric acid, react it with benzene, the product is going to correspond to ending up with a nitro group, NO2, attached there to the ring. So let's take a look at the mechanism for this. First things first, generate a stronger electrophile. And that is going to involve the mixture of our sulfuric acid and nitric acid. If we look at the pKa's of those two molecules, sulfuric acid and nitric acid, sulfuric acid is the stronger acid. It has the lower pK value. And so what it's going to do is it is going to lose a proton to nitric acid. So oddly enough, in this reaction mechanism, nitric acid is acting as the base. It's going to gain a proton in this step because it is the weaker of the two acids, and therefore it's going to act, instead of as an acid, it's going to act as a base. And so first step of generating a stronger electrophile in this particular scenario, we will go ahead and draw out sulfuric acid, H2SO4. This is one of the few times when I'm going to draw out the complete structure for sulfuric acid rather than just abbreviating it so that we can see exactly what is going on here. So we have our two OH groups bonded there of sulfuric acid. We're going to react it with nitric acid. The complete structure for nitric acid in its most stable resonance structure is that we have nitrogen double bonded to oxygen, and then that nitrogen has two bonds to oxygen. One of those is an OH group, the other is an oxygen anion, so I'm going to put that as O minus there, and our nitrogen with 4 covalent bonds is N plus. So looking at this, our sulfuric acid is going to act as the acid here because it has the lower pKa value of these two substances. And on the other hand, the nitric acid is going to act as the base because it is the compound with the higher pKa value. It is the less acidic, and therefore it's what is available to act as a base. So what's going to happen here is that we will take a lone pair of electrons from the hydroxy group of our nitric acid, and those are going to come over acting as a base to grab one of the protons from sulfuric acid. Due to the symmetry in sulfuric acid, doesn't matter which of the two hydroxy groups is attacked, but we're going to grab a proton from that sulfuric acid. So the outcome of this is that we will have, as a consequence, our deprotonated sulfuric acid as the conjugate base. So I'm going to go ahead and draw that with our oxygen anion here. We will also generate, as a result of this reaction, our protonated nitric acid as the conjugate acid here. We'll have OH2 on this right-hand side of the molecule with a positive formal charge on that oxygen. And then we have an oxygen anion over here, like so, and a positive charge finally on the nitrogen here. Now, this conjugate acid product that we have created here is relatively unstable and relatively reactive. And what's going to happen here is that we have water, which we recognize water as a very good leaving group in general. And so what will happen here is that the water leaving group is going to be very favorable to break away, because as that water leaving group breaks away, what can happen is that this oxygen lone pair of electrons can come over to form a nitrogen-oxygen double bond there to ensure that nitrogen is able to maintain its complete octet, thereby yielding our product of this step. And it is this process that's occurring here that allows us to explain why we pull the proton from our sulfuric acid onto the hydroxy group rather than forming a bond to the oxygen anion over here. It's because once we get over to here, we're able to use that water as a very favorable leaving group to, in simultaneous fashion with the oxygen lone pair, coming over here and making the nitrogen-oxygen double bond. And so the consequence of that is we end up with water, which is broken away as the leaving group, and then we also end up with NO2. And in our NO2, the most stable, favorable resonance structure for that is going to be exactly like I have drawn here, where we have our two covalent bonds on each side of the nitrogen, giving the nitrogen a +1 formal charge, and our net charge there being +1 overall. And keep in mind, as is always the case with mechanisms, we are conserving the net charge here for what just reacted. So when we reacted our starting substance here that I'm highlighting with my laser pointer, that had a net formal charge of +1 because we had two positive charges offset by just one negative charge. So the net charge was +1. And then in our product here, our net charge overall on the product side of this equation is +1 as well. And the key to this, and the reason why we went through these two steps here, is that we have generated, as a consequence of that, this NO2 with a very electrophilic nitrogen atom. So we have generated here a very nice electrophile. So I'm going to label that as EL, and I'll go ahead and highlight it as well just to remind you that this nitrogen is going to be able to act as a very good electrophile. And that was the purpose of step number 1 here, or part 1 of the reaction, is that we generated a stronger electrophile, specifically that NO2 plus electrophile. And that is going to help propel the rest of the reaction along, because we have a very reactive electrophile due to the fact that we have that positive charge on nitrogen. The nitrogen is very eager to have some electrons come in and attack it. So I've zoomed out just a bit so that I can fit everything onto the screen here. Now we will go onward to part 2 of the reaction. In part 2, that is where we said that the pi bond was from the aromatic compound was going to attack the electrophile to yield the Arenium. So I'm just going to label this over here as the pi bond from the aromatic ring attacks the electrophile, that's going to be the nitrogen of NO2, to give the Arenium product. That was our positively charged carbocation intermediate. So let's go ahead and write this out. So we'll have our benzene ring, and we will take any of the pi bonds from that ring, whichever one we want to work with. They're all symmetrical, so it doesn't matter which one we use. That pi bond is going to come over, and it's going to attack the electrophilic nitrogen atom. This electrophilic nitrogen is very eager to react because it has that positive formal charge on it, making it strongly electrophilic. So the pi bond comes over, forms a covalent link to the nitrogen. That's going to force the pi electrons from here to come over onto the nitrogen so we don't go over the octet rule. And then our product of this step is going to be our so-called Arenium cation, where we still have those 2 hydrogen atoms directly bonded here and here. Now we additionally to one of those 2 hydrogens, take your favorite, pick whichever one you want, we'll have the NO2 group attached to it. So I'm going to put the nitrogen in. Nitrogen still has a pi bond to one of the oxygen atoms, so I'm going to go ahead and draw in that oxygen and its lone pairs of electrons. And then the other oxygen is now present as a nitrogen-oxygen single bond because we had to move that pi bond out onto the oxygen in order to avoid going over the octet rule for the nitrogen. And so now we have our oxygen, and it will have not 2 sets of lone pair electrons, but now 3 sets of lone pair electrons because we had to move those electrons from the pi bond out onto the oxygen. So remember to plug in that negative formal charge on the oxygen, positive formal charge on the nitrogen. This is your most stable resonance structure for this because it has maximized the number of covalent bonds in the molecule and the number of atoms having a complete octet. So now I'm going to plug in my positive formal charge, which will reside right here. This is why we refer to this as our Arenium. The Arenium, derived from the name arene for an aromatic compound, with the IUM indicating a positive formal charge, much like ammonium has a positive formal charge. The IUM indicates a positive formal charge. Positive formal charge is going to be at one of the carbon atoms of the ring, and we're circling that right here with my laser pointer. So now we come onward to the third and final step of the reaction, which is where we, as the directions for general electrophilic aromatic substitution indicate, we're going to lose a proton from the Arenium in an elimination type reaction mechanism in order to restore the aromaticity. So let's zoom out and take a look at that. So I'm just zooming out a bit to give myself enough space to do that final step of the mechanism, where I'm going to go ahead and put in brackets here what in the world I am doing here. And what I am aiming to do here is lose a proton from the Arenium to restore aromaticity. This step is very favorable because of the fact that aromatic compounds have immense stability, as we learned in the last chapter. And so by restoring aromaticity, this reaction is very much energetically favorable. And so that is why we are doing this type of process here to restore aromaticity. So we'll go ahead and redraw our Arenium ion. That's what I'm doing right now. Plugging in my lone pair electrons and formal charges. In other words, dotting all my molecular I's and crossing all my molecular T's here. Positive formal charge on the carbon of the ring. And now, in order to restore that aromaticity, what we need to do is remove a proton from the position that is beta to the carbocation. So if we consider this carbocation to be the alpha carbon, the carbon adjacent to it is the beta carbon, and the hydrogen there is the beta hydrogen. So it's a beta elimination type reaction here. And so what will happen then is that we have a base come in and grab that proton. When that proton is removed, that's going to force the electrons from the bond here that I'm highlighting to come over and restore the aromaticity in the ring in an elimination type process. So what will we use as our base here? We have two choices for what we can choose to use as the base. One is that we created water back here when we were doing our reaction of sulfuric acid and nitric acid. So we could use that. We could also use our HSO4 that I'm circling right here, which was the conjugate base that resulted from deprotonating our sulfuric acid. So either of these, HSO4 or H2O, will each work as our base for this last step of the reaction. So pick your favorite one there. If you go with the conjugate base from sulfuric acid, you would want to take the oxygen anion and use that as the base to grab a proton from the beta position of the Arenium. If you use water, we're going to use the lone pair of electrons from the oxygen for that. And in the interest of, I will call it laziness or space here, I'm going to use water, H2O. Bring that lone pair of electrons over to grab this proton from the beta position, forcing the carbon-hydrogen bond to break and those electrons to come over to restore the aromaticity of this system, because aromatic rings are very, very hard to permanently destroy due to the fact that they are so stable. Their formation is very favorable. And so we'll go ahead and write out the full Lewis structure of our nitro group, at least for now. Generally speaking, when you are writing this out as a product, you're welcome to abbreviate as NO2 like I've done up at the top here and I'm highlighting at the top of the screen. But since we're writing out a mechanism, I'm going to show all of the lone pairs and formal charges and all that explicitly. So this would be our final product of the reaction. We have created our final nitrobenzene product by going through this systematic step-by-step process that we will see over and over and over again, where in general, we are always, as our first step, generating a stronger electrophile, which we did in this case by a two-step reaction mechanism initially, where we took, first off, our sulfuric acid, reacted with nitric acid, which was acting as a base. The base, nitric acid, grabbed a proton from the acid. And then very quickly, this intermediate that formed of H2NO3 lost water because water is a very favorable leaving group, and that resulted in the formation of this NO2 as a very good electrophile for the rest of the reaction. So our process of generating a stronger electrophile was in and of itself a two-step process here. So we could think of this as a two-step mechanism for creating a stronger electrophile. After we had accomplished that, the next thing that we did was in part 2 here, step 2, we had our pi bond come over and attack the electrophile to give the Arenium cation. And so that was what we were doing in step 2. And then following the general guidelines for what we do in step 3 of these EAS reactions is we lose a proton from the Arenium at that beta position in order to restore the aromaticity. And we're going to see this pattern over and over and over again as we do these EAS type reactions, where we will be plugging in as our variable a bunch of different types of electrophiles. And so really the main thing that's going to change between mechanisms that we'll look at will be the first step or the first part of the reaction mechanism that generates a strong electrophile. And then from there, we'll recognize what the electrophile is and go through steps 2 and 3, just following this pattern that we see here.